Hello and welcome back to Unit 3. In this part, we are going to introduce 2D projectile motion. And to begin with, we're going to look at a simulation. When you open that link, which I will put up on Brightspace, it opens this window. And if you click in there, you have lots and lots of possibilities, but you just want the first one. So first, let's lower this down a little bit and angle it up a little bit and fire the cannon and just see what happens. As you can see, the path of the projectile is a parabola. Now, one thing to notice is that this is a perfect parabola because there's no air resistance at the moment. If I turn on air resistance, then the path is still vaguely parabolic, but it doesn't go as high, nor does it go as far. In this unit, we are going to assume that air resistance is negligible. We do not have to consider its effects on the path of a projectile. On the next slide, I have a link to a video that shows the effect of air resistance on dropping bowling ball and dropping feathers, and showing that when you remove the air from the room, the two items fall at the exact same rate. But for the moment, let's get back to this. I'm going to clear the paths, turn air resistance back off, and I'm going to lower this cannon down so that it is firing from ground level. And the first thing I'm going to do is fire at a 45-degree angle. Okay, so there is a beautiful parabola. I'm now going to increase the angle of the cannon to 60 degrees and compare the paths. So at 60 degrees, we can see that the projectile goes higher than it did at 45 degrees, but it does not go as far. If I lower the cannon down to 30 degrees, again, I don't go as high as the 45, and I do not go as far, but if you look at the 30 and the 60-degree paths, they hit the same mark. Any angle less than 45 degrees will not go as far as a projectile launched at 45 degrees. And angles that are symmetric around 45 degrees will hit the same spot. They will have the same range. One of the examples that is completed in the next parts shows why that is the case. Going back to the PowerPoint presentation, as I said, here is a link to a YouTube video that shows the bowling balls and feathers dropping. I will post this link again to Brightspace so you can watch that video on your own. Now let's consider the equations for 2D projectile motion. Remember that the position of an object can be considered as a horizontal position in the x direction, plus a vertical position in the y direction, plus a position in the z direction. Now we're working only in those two dimensions are typically x and y. As long as we can separate the motions, meaning that what changes in the y direction does not affect how the x direction changes. Or if you want to think about it in terms of calculus, if I take a derivative with respect to x, the derivative of y would be 0. Okay. In that event, then I can take my projectile motion equations that we derived a couple parts ago and write them as two separate pieces. So horizontally, I have these three equations. And notice there's lots of subscripts here because I'm going to have a horizontal velocity and I'm going to have a vertical velocity. I'm also possibly going to have a horizontal and a vertical acceleration. So those also needed subscripts. Okay. Typically, when working with 2D projectile motion, we let the horizontal acceleration be 0. That removes 3 terms, one from each equation. And we can see that the 2 bottom equations horizontally tell us the exact same information, that the horizontal velocity is constant. Okay. So in reality, all we have left is this little bit of the top equation horizontally. Vertically, we've got to keep it all. Okay. Notice that between the horizontal dimension and the vertical dimension, the tie-in is time. These two motions, horizontally and vertically, do happen at the same time. So we can use information in one dimension to help us find values in the other. Lastly, when are these equations valid? We have to have a constant acceleration. That means we have to be near the ground. By being near the ground, we can say that the vertical acceleration is due to gravity, so 9.8 meters per second squared, downward. Okay. And we have to neglect air resistance. As soon as we put air resistance in, the horizontal acceleration will not be 0, and the assumed separability of our equations would not happen as well. This concludes this part.